Okay, so in the last lecture, we arrived at this idea that we could have, well, we know that the normal stresses and the shear stresses vary, and we saw that in our plots of our transformation equations. But the natural conclusion from that was that there could be larger values of normal stress and indeed shear stress than the ones that we are seeing on a particular set of planes. And so what we're going to do in this lecture is we're going to start talking about principal stresses and principal planes. Now, principal stresses, as a definition, first of all, are the maximum and minimum values of the normal stress. Okay, at a particular point. And these stresses develop on what are called principal planes, right? And these are just the planes, the two mutually perpendicular planes on which the maximum and minimum normal stresses develop. So in this lecture, we're going to derive a couple of expressions for the principal stresses and indeed the principal planes. And then we're going to confirm our expressions by plotting these values onto the plots of the transformation equations that we saw previously. Okay, so as a starter here, let's just get down a couple of definitions, the principal stress and the principal planes, very straightforward. So it's the maximum, these are the maximum and minimum values of normal stress. And then the principal planes related are the inclined planes on which the principal stresses act. Okay, and as I said, our objective here is to find the principal stresses and the orientation of the principal planes. Okay, so we're going to start off here. Let's start off by focusing on principal stresses. So let us first of all jot down the equation, the transformation equation we have, which is telling us how the normal stress varies as we change the angle of orientation of a plane. So we saw this previously. Okay, so what is it? It's an equation that is showing us essentially a curve. And what do we do when we want to find the local maximum or minimum of a given equation? Well, we differentiate it, because in differentiating the equation, we're going, well, in this case, we're going to differentiate with respect to theta. And what that's going to do for us is give us an expression for the slope of that curve at any given point. And again, we've got an equation that's doing something, that's describing a wave, something like this. And if I was to differentiate that equation, I would end up with an expression that gives me the slope at any point. And if I want to find the local maximum, what I would do is I would identify the point where the slope of a tangent to the curve, so a slope of a tangent to that curve at that point there is going to be horizontal if that's the maximum point. So that's what we're going to do here. And we use this little trick all over engineering and various different derivations and things. So the first thing, as I say, I'm going to do is I'm going to take d theta of sigma x1, which is just going to give me an expression that describes the slope of this equation. So straightforward enough differentiation here. Okay, and again, just to reinforce the point here, this is the slope of the curve. Okay, let me see, where to next? What we're going to do is we're going to say let that equal to 0, right? So let the slope equal to 0, and in doing so we're identifying the location essentially of that maximum, that local maximum in the curve. So a little bit of tidying up here, just letting that expression equal to 0. Okay, so ultimately we can simplify this down into the tan of 2 times theta is equal to 2 times tau xy over sigma x minus sigma y. Okay, what is that? If we think about what that actually is graphically, let's just say graphically, what we've actually got here is we can imagine an angle, some angle in here. Let's call that 2 times theta. And I'm going to give it the subscript theta p here because it's going to be a principal angle. Now, if the tan of 2 theta p is equal to this guy here, well, that means that if I'm thinking about this as a triangle, well, then the length of the opposite side, I could say is tau xy, and the adjacent side is going to be sigma x minus sigma y over 2, and then so of course is a right angle triangle, and so we can say the hypotenuse is equal to the square root of the other two sides squared. So that's going to be sigma x minus sigma y over 2 to be squared plus tau xy to be squared. It's also worth remembering here, that we have an angle 2 theta there, but equally we could have an angle 180 degrees separated from that, apart from that, of 2 theta p as well. So there are two possible angles, right? So let me just make a note down here just to say we actually have two values of the angle 2 theta p that can be obtained, and they're both 180 degrees apart. All right then, so what does that actually mean? Well, that means that there is an angle there is an angle, or two angles. The angle theta p has two values, 90 degrees apart, just dividing across by 2. Okay, and these two angles are my principal angles. Okay, and it makes sense to us because we're going to have the maximum value of the normal stress and the minimum value of the normal stress. Remember, the sum of the normal stresses on two perpendicular planes must be constant, right? So if the maximum value is occurring on one plane, well then the value on the perpendicular plane to that must be the minimum value. Okay, and so when we know, because we've defined it at the start here, that the maximum and minimum value of normal stress occur on principal planes, they're principal stresses. So these values, it makes sense to us now that the values of theta p that we've identified, these two possible values, right, it makes sense to us that they're 90 degrees apart. Okay, so let's just sort of tease that out another little bit, and we'll say for one value of theta p, remember there's two of them, for one value of theta p, sigma x1 is going to be the maximum principal stress, and for the other value of theta p, sigma x1 will be the minimum principal stress. Okay, so we got two angles now we've worked out, and one of them is going to be the angle upon which the maximum principal stress, or the maximum value of the normal stress occurs, and we're going to define that as a principal stress. And then on the angle on the side, on the face that's 90 degrees separated from that or rotated from that, we're going to get the minimum principal stress. Okay, and so we've made this point already, but it's worth sort of putting it down here in black and white. Principal stresses occur on mutually perpendicular planes, and that's a direct, if you like, consequence of the fact that the sum of the principal stresses on adjacent perpendicular faces is constant, right? So if we've got the maximum occurring on one face, well then we must have the sum of the two is to be the same, is to be constant. Well then we must have the minimum possible value occurring on the face that is sort of mutually perpendicular to that. So let's just jot that down. So the principal stresses occur on mutually perpendicular planes. Okay, so let's just underline this term, mutually perpendicular planes. And of course we can see that when we go back over and we look at where we plotted the transformation equations. Now let's just ignore the red line here for a second, because that was the shear stress. We're not thinking about shear stress right now. We're just looking at the blue line and the green line. So the blue line was the stress sigma x1, right? So that was just the normal stress developing on one plane, right? And then if I was to look at so let's imagine the vertical right hand plane of a rectangular or square element, and then the top plane would be the mutually perpendicular plane adjacent to that, and so that would be the green line here would give us the stress on that mutually perpendicular plane, right? So if we come along here and we say to ourselves, right, well, if I look at the blue line here, the maximum value of the blue line is occurring somewhere around the 30 degree mark, right? So somewhere we're going to find out, and we'll confirm it now we start doing some calculations, but somewhere we'll find out that somewhere here between 20 and 40 degrees, let's say 30 degrees, the maximum value of the normal stress on that plane occurs. Now at the same time that I'm on a maximum for the stress occurring on that plane, if I look at the adjacent perpendicular plane, which is going to be the stress on the stress sigma y, that's described by the green line, right? What am I going to find? I'm going to find that at the very same time sigma x1 is at a maximum, well then sigma y1 is at a minimum. Okay, and remember, this line here, this green line here, is the stress occurring not at 30 degrees, but the stress occurring at 30 plus 90, because it's on the mutually perpendicular plane, right? And so that would be the stress. The green line at this point here is giving me the stress on a plane at, let's say, 120 degrees. Okay, so it can be difficult, certainly initially when you're looking at this stuff, to try and relate this back to our little stress element. So let's relate what we've just discussed, right? What I've just explained between the maximum here and the minimum here. Let's relate that straight back to an element, right? So I said the maximum principal stress is going to occur on a plane that's orientated at about 30 degrees. Okay, so what does that actually mean? Well, if I was to draw my element, let me sketch an element on here like this. And I'm going to draw on what would have been a set of axes orientated aligned along, let's imagine, a global XY axis. And so this is our reference axis here, right? So that's going to be X and Y. And I said that if I had a plane orientated at 30 degrees, that would be, let me see, if I draw on my rotated set of axes, let's call that the X1 axis. And let's call this the Y1 axis. I just said 30 degrees eyeballing that from the graph, right? So what that graph has told me is that on a face orientated at 30 degrees, I'm going to have the maximum value of normal stress, and we typically call the maximum value sigma 1. Okay, so that's going to be the maximum principal stress. And then we said at the same time, on a plane orientated a further 90 degrees around, so let's say 120 degrees, I'm going to have the minimum value of stress. And those are the 2 points that we saw on that plot, right? So let's call that sigma 2. Okay, so this face, right, this face here is orientated at theta equal to approximately 30 degrees, and this face here is orientated at theta equal to approximately 30 plus 90 is 120 degrees. And that's why when we saw our plot and we plotted how this guy varied with theta, sigma x1, I've relabeled it sigma 1 here, but sigma x1, we saw it had a local maximum. It had a local maximum at about 30 degrees. And then when we compared that with the plot for how this guy varied with theta, which we called sigma y1, relabeled here as sigma 2, we found that at the very same time this guy was at a maximum. Well, then the graph describing how he changed, right, with angle was at a minimum, right, was down here at a minimum at the very same time. Okay, and all that is the two principal stresses, the maximum principal stress and the minimum principal stress. Okay, and then this is it related back to our 2D stress element. Okay, so hopefully I haven't made that any more complicated than it needed to be. So let's actually now tease this out a bit more and actually work out our expressions, some equations for sigma 1 here and sigma 2 here, so we can straight away determine what the maximum and minimum values are without having to actually plot this thing out. So if the tan of 2 theta p was this guy over this guy, well then the cosine is going to be the adjacent value, which is going to be this guy divided by the hypotenuse, this guy here, and the sine is going to be this guy over the hypotenuse, this guy. So let's actually state that here. Now, where is this going? Let's take these expressions for sine and cosine of 2 theta p and sub these two expressions back into our transformation equation. Transformation equation 1, right? So sub them all the way back into this equation here. Okay, so if I do that then, what am I going to end up with? I'll end up with sigma x1 being equal to the following. Okay, so sigma x plus sigma y over 2 plus sigma x minus sigma y over 2, all multiplied by sigma x minus sigma y over 2 times the hypotenuse, plus tau xy times tau xy over h. Right, do another little bit of simplification here. So we'll just say simplify. So what do we end up with? Sigma x1 is equal to, now let's do another round of simplifying. So we're going to get the following: sigma x plus sigma y over 2. Take the h out, so we're going to get plus 1 over h. Now when you take the h out, what you're left with is this: sigma x minus sigma y squared over 4 plus tau xy. What is that? That is h squared. So all you really have here is h squared over h, which obviously comes down to just being h. So you end up with sigma x1 is equal to sigma x plus sigma y over 2 plus h. Okay, what is that? That is the maximum value. That's the maximum value of normal stress. Okay, so we're going to rename that sigma x1 to be sigma 1, which is typically the subscript we give to the maximum principal stress. So that's equal to sigma x plus sigma y over 2 plus, and we'll put in the full expression for h here, and that guy there boxed up is our handy expression straight away for the maximum principal stress. Now this is really useful for us because we don't need to be worrying about angles here initially. All we need to get, in order to get the maximum principal stress, all we need is a value of sigma x, the corresponding value of sigma y, the value on the perpendicular plane, and then the shear stress, tau xy. Once we have those, we can work out what is the maximum value of the principal stress, or the maximum value of normal stress, which we call the maximum principal stress. Now, we can use this other fact that we've observed, the other fact, which was that the sum of the stresses on mutually perpendicular planes is constant. So we can say sigma 1, the guy we just worked out, plus sigma 2, which is the second principal stress, which is obviously going to be the minimum value now, which we're going to try and find, that must be equal to some value sigma x1 plus some other value sigma y1. We'll assume we know this guy, we know this guy. If we know those two and the corresponding shear stress, we can work out this guy. And so we can rearrange to find sigma 2. And then you just plug basically this expression in for this, and what do you end up with? You end up with sigma 2. The minimum value of normal stress, the minimum principal stress, is this. So that's our minimum principal stress. So we've now worked out some key values here, right? The principal stresses are really important values to us as engineers, so that we need to know what are the maximum values of stress that develop. And now we've worked out a nice handy expression. We've got an expression for the max, and we have an expression for the min. All right then. So let's just package those up and say the two principal stresses, therefore the two principal stresses are equal to, let's go, sigma 1, 2 is equal to sigma x plus sigma y over 2. What is that? Sigma x plus sigma y over 2. That's just the average of sigma x and sigma y, right? Sigma average, you'll often see this written as. And then plus or minus our h, right? Whatever the hypotenuse of that right angle triangle was. And if we draw that out or write that out longhand, it's the following. All right, this is pretty fundamental. This is pretty important to us, because what this is telling us is the maximum and minimum values of normal stress. I keep emphasizing this because it's really important to us. So let's just go ahead and calculate some numerical values for these and plot them onto our equation, or onto our plot rather. So now, and let me just put a box around this, right? This is what I'm about to plot onto my graph here, right? So I want to calculate sigma 1 and sigma 2. So I want to calculate this guy, which I'm just going to call, in my code, I'm just going to call that sigma average. And then I'm going to want this guy as well. And in my code, I'm just going to call this h. So really what we're going to be able to say here is that sigma 1, 2 is equal to sigma average plus or minus h. All right, so let's implement it. So let me see, first thing I want to do is calculate, let me give myself a quick heading here, just to say we want principal stresses. All right, let's work out sigma average. Well, what is it? It's going to be sigma x plus sigma y over 2, or in other words, 0.5 times sigma x minus sigma y. All right, that'll do. And then, no, it's not a minus, it's a plus. Sigma x plus sigma y over 2. Then we're going to want h. Well, h was that slightly longer expression. It was the math.sqrt, so square root of something squared plus tau xy squared. And that's something, that first something squared was something over something else. So it was sigma x minus sigma y over 2, sig x minus sig y over 2. And that's the expression for h. All right, now let's work out the maximum principal stress. Sigma 1 for this case is going to be, this is why I like breaking it up like this, because it makes this next expression very straightforward. It's just sigma average plus h, and we can say that the smaller principal stress is just going to be sigma average minus h. All right, now we can work out the principal planes. Don't forget, we have all the information we need to work those out as well. So let's say theta, we're just going to call it, let me say theta 1. So theta 1 was going to be 0.5 times the tan inverse. So that's going to be from the math library. We want the arctan or tan inverse. So that's a tan. Now what is it? It's going to be 2 tau xy over sigma x minus sigma y. So it's going to be something over something, and that first numerator is going to be 2 times the tau xy, and then this in the denominator is going to be sig x minus sigma y. Now I don't really want to deal with that in radians. In fact, I'm going to need an equal sign there. I don't want to deal with that in radians. I'm not a huge fan of those, so I'm going to change that to degrees. So that's going to be theta 1. Let's give that theta 1d. All right, so we're going to say that that's going to be whatever theta 1 was times 180 over pi. And then I'm going to want the other principal plane, which we know is 90 degrees, is at 90 degrees to the first one. So we'll say theta 2d is going to equal theta 1d plus 90. Simple as that. All right, so now let's just print out a few statements here just to really clarify what it is we've calculated. So what have I got? I'm saying here in a print statement, a string that says the principal angle, and I'm just calling it theta underscore PA for now, right? Because I'm not actually tying either of these angles to either of these principal stresses just yet, right? So I'm just saying theta, one of the principal angles, let's just call it theta PA, is equal to 1, and I got a little placeholder here, and then I call format on the end of my string, and then I pass in 1 as being equal to a rounded value of theta 1d. All right, and then I will do the exact same thing for the second principal angle, just change it to theta 2d, and then we're going to say the maximum principal stress is sigma 1 and the minimum principal stress is sigma 2. Let us run that. So shift enter, see what we get. Of course we have an issue. Math isn't defined, and that's because I haven't run this from the top yet. Okay, excellent. So what are we seeing here? We're seeing that the principal angle, right, one of the principal angles is 31.7 degrees. Makes perfect sense to us because we'd eyeballed this earlier and we said that's about 30 degrees. But sure enough, it's actually a little bit more. It's 31.7. Kind of makes sense because it looks slightly ahead of the midpoint between this vertical line and this vertical line. Okay, we like that. And of course, the other principal angle is 90 degrees advanced from that. So that's just 121.7. And that also makes sense because if we look at when sigma y becomes a maximum, of course, it's 90 degrees on, which is about here, which is 121.7. All right, then. Now, the maximum principal stress is 1.46. Again, yeah, just shy of 1.5 there, so that makes sense. And then the minimum principal stress is minus 0.21. So that's going to be a compressive stress because it's minus, and we've got our value here, and that roughly tallies with minus 0.21. So if we want to be a little bit more explicit in identifying these within our graph here, these values, these key values, let's just plot some guidelines on. That's one of the things I like to do just to make this easier to see. So I'll just say guidelines for principal stresses, right? So I'm going to say axes dot plot. What am I plotting? Well, I want to plot a horizontal line here at the level of the maximum principal stress. So I'm going to say the x coordinates of this horizontal line are minus 180 and plus 180. The y coordinates are the same. It's a horizontal line, so it's going to be sigma 1 and sigma 1. And would I like this to be in a color? Yeah, let me make this color cyan, because why not? And then let me make it a dashed line. So I'll say line style is equal to a dashed line. What does that give us? Okay, excellent. So that's a horizontal line at the level of the maximum principal stress. And exactly as we'd expect, it is just touching the maximum value of our blue, well, of both our blue and our green lines here. But what that dashed line, horizontal dashed line is, it's a tangent to this blue curved line, right? This blue sine wave, it's a tangent to that sine wave at exactly its maximum point, all right, which is the maximum principal stress. And let's plot, just for completeness, let's plot the minimum principal stress. Same exact statement, except this time we want to plot 2. And what do we want? Let's make this lime. What do we have? There we go. There's our lime, which is the level of the minimum principal stress, just touching off the bottom of each of these sine waves. Perfect, that's okay. And let's just plot on our angles. So now I want a vertical guideline. Right, so this is going to be theta 1d, and then what values of y do I want? Let's just make it span from minus 1.5 to plus 1.5 in the y direction. What color do we want? Let's make it red. Okay, very good. So what we're saying here is the angle, the first angle, theta 1, theta 1a I think we called it, or theta PA, sorry, here it was 31.7, right? That 31.7 is represented by this vertical line here, and that is corresponding here with the maximum value of the principal stress. So the maximum value of the principal stress, which is 1.46 newtons per millimeter squared, is occurring on a plane that is orientated at 31.7 degrees to the horizontal. Okay, and that's essentially that point there. All right, and let's plot let's plot theta 2. Okay, let's plot theta 2, and of course it's just going to be 90 degrees further along. And there you have it. Okay. And so the minimum value of principal stress is occurring when theta is equal to 121.7 degrees. Okay. So if I was to keep rotating that plane, this plane on which sigma 1 is occurring, when that plane is orientated at 31 degrees, if I was to keep rotating that plane, it would have to continue rotating all the way around until that plane was down at 121 degrees, and that's when the value of the stress on that plane would be a minimum. Okay, now that's one way of looking at it. The other way of looking at it is by saying here is the maximum value of stress on that plane, and at the same time another plane exists that sigma y is acting on, and at the same time that sigma x is acting on a plane of 31.7 degrees, sigma y is acting on a plane that is 90 degrees rotated from that, and it has a value of minus 0.21. So let's just look at our element here, just to really tie these two plots together, right? Or the plot and this diagram. So we said we have one face orientated at 32 degrees, let's just call it, and we said the stress on that face was sigma 1 equal to 1.46 newtons per millimeter squared. Now at the very same, and that was this point here, right? That was that point there. Now at the very same time, we have a stress acting on a plane orientated at 90 degrees to that, which is this plane here. And if we look at the stress sigma y, what's the value of the stress sigma y? Well, it's at its minimum value down here, which was minus 0.21 newtons per millimeter squared. So at the very same time that I have sigma 1 acting on the red plane, I have sigma 2, the smallest value of stress, I have that acting on the y plane. So that's sigma 2. Okay, now if I was to, so far so good. Now if I was to take that element and I was to continue rotating that actual element around 90 degrees, right? So if I rotate the element around 90 degrees, now what are you going to end up with? You're going to end up with a shape like this. But now the red plane that was here is now here. Okay, and don't forget your set of axes. Your set of axes has also rotated around. So now that's your x1 axis, right? And now that's your y1 axis. So if you rotated your element around a further 90 degrees, that would now be where our green plane is. And what's the value of x1 now that I've rotated further around by 90 degrees? Well, let's come back over to our plot. Sigma x1 has now gone all the way down, because remember this plane is now orientated at 120 degrees. It's now down at its minimum value. Okay, it's down at its minimum value. So now the stress acting on this plane is now a minimum. So we'll say that was a max and that was a min. Now this still has to be a min, right? And sure enough, that's what our plot of the transformation equation is telling us, that when we rotate that face around to 120 degrees, sure enough, it has to be a min, right? It has to be a minimum value, the minimum principal stress. And now this is going to be the maximum principal stress. And it makes sense because the two diagrams have to agree. So now we understand the maximum and minimum values of principal stress. They occur on two mutually perpendicular planes. If I have the max on one plane, I must have the min value on the corresponding plane, the plane orientated at 90 degrees to it. So I think we probably have enough covered at this point. What we'll just observe now, and we'll tease this out in the next lectures, we'll just observe the fact that our shear stress happens to be, or appears to be, zero, right? It appears to be zero on these principal planes. And in fact, the shear stress is zero on principal planes. There is no shear stress acting on these principal planes. And we're going to go ahead and confirm that in the next lecture.